All right, 7:30. Let's get started. I believe so far we have 58 participants. I can see. Okay, that's good. And welcome back post midterm sessions. I'm sorry that I had to cancel the last meetings for some urgent reason, but we'll try to pick up these two lectures. Like the topics are fairly easy in the scale of what we were doing till lecture 11. And these were lecture 11. I think most of you will admit that that is kind of so far most intense topic. And after that, we'll have, with these two topics are very light in the sense it is more like a theoretical, uh, and it is just a conceptual theoretical discussion. After that, we'll pick up, excuse me, another concept like pipeline that is a bit involved, that concept itself. And after that, I think what's in our pipeline. We'll review some abstract concept and architecture for the parallel systems. Um, yeah, so theme from now onwards that we already done a basic processor design which has some runtime. Now we want to improve the runtime, improve the performance, as we say, improvement the performance, and we'll see different techniques and system level and processor level techniques, how the performance is improved. So those are our topics from going forward, and it will become more abstract in the nature that we probably won't be dealing with hands-on example like the lecture 11 we did. Like both project 2 and project 3 are practically reflection of what we actually discuss on the topic lecture 11 topic. But anyway, let's begin with post midterm sessions. And we have like first topic was more like an instruction set architecture, little bit on discussion on the CISC and the RISC. I hope you guys have reviewed that. And I don't see any question on those that modules on the discussion topics. Um, what are the important things there? Like conceptually, like big Endian, little Endian, those concepts, I hope you have picked them up from your CS147 or equivalent classes. And there are, what are the different modes of data access, like there can be like our CS147 DV has only limited set of data access mechanism, but in the real world, there can be more depending on which processor, which architecture we are talking of. So we have discussed some other extra data access mode in this specific topic. And also we talked about a little bit on the two classic example of architecture, CISC and RISC, complex instruction set computer versus reduced instruction set computer. And this is like two classes of people who believe one is better than other. Okay, like the tent risk tent people, they that clan thinks CISC, we don't need CISC. CISC is just like overhead on the processor design, and it increases the complexity, so keep it simple and that would be a better performance. Whereas the CISC clan actually thinks that they are better because they actually provide more complex support, so that programming, or at least the compiler designer life, is easier, and it has a compact memory footprint and so on and so forth. In reality, neither of these clan is right or wrong. Like it's just a philosophy. Okay, it's just a philosophy. No one is right, no one is wrong. And in fact, in the real world, people actually learn to like share ideas between them, and internally they can go with some of the like let's say CISC style design can borrow some risk concept and other way. It all depends on which is the target market for your processor, and best architecture are picked up. So in that sense, that classification CISC and RISC is like blurrier, becoming blurrier day by day. like probably down the line, like it probably won't have any significance. That's what my projection is. But anyway, that's too theoretical. Let's do some practical example, especially on the data access mechanism, to little bit review on them, unless you have question for me right now.
Oh, hey, Professor, can you hear me?
Yes.
So a bunch of people were discussing this, and we thought it might be fair possibly to have an extension on the project because we had a midterm followed by a class delay, like a canceled class. So I just wanted to know how you felt about that.
Thank you for bringing this up. I think one student at least contacted me about this one. Answer is no. Why answer is no? Because if you look at the milestones set already by 19, we should be on the testing phase, right? And I should, I was expecting more question on the project before that. So I'm assuming you guys are on track, and that's why, no, there is no extension.
All right, that's fair. Thank you.
Okay, anything else? So one more point on this extension, right? Remember, like your project 3 is equally challenging. Okay, so if you are extending on the project 2, that means you are eating up on the project 3's time. So you better finish it by the deadline. That will give you a good advantageous edge on the project 3 onwards. Okay.
Can I ask a clarifying question for
Yeah.
project 2? So for project 2, we have to create we have the state machine, and every time the state changes, we change all of the signals. We change like the signals there, but so so the state machine changes when the clock changes, but when the clock changes, the memory and the register files also also like uh, do their calculations at that point. So at that moment when we when we do the change the control signals, like if I change the control signals already, then how then are these control signals that I use, like I do like a write like write equals 0, read equals 1 for like the register file, is that affecting right at that moment? So when the clock changes, the control signals change, and the change in control signals, does it affect the memory and the register file at that point? Like
That's a good question. That's a good question. So basically, what we are following in this simulation environment is called a zero delay model. Zero delay model means as soon as you are issuing those signals, it is available to the other components. Okay, so if other components are kind of active as, let's say, positive edge of the clock, it should get that triggered immediately. Okay, so that's a zero delay model. But in reality, it actually basically at the clock edge you issue, that is being accepted by the other component in the next clock cycle because there is this delay involved there. But right now, let's not get into that complexity, and it should be like zero delay whenever you are issuing that. And if it is right on that clock edge, your other components should start responding at that.
okay, okay, that clears it up. Also, I have another question. It's about like using, so I have instruction fetch, then I have instruction decode. In instruction fetch, I set the memory to read so that it reads from the program counter. So for that whole cycle, since you said it was zero delay, then I would have in that memory that data, that read data. so on the instruction decode, immediately I'm going to like,
Receive
so
that instruction, whatever read from the memory. You should.
yeah, so when I do the control signals, that am I taking the instruction, like the data from the previous cycle of the memory, like uh, so am
Yes.
I taking it? Oh, so whenever I'm taking the data for the instruction register at instruction decode, that means I'm taking that data from like the previous, like the very end of the previous cycle of
Right, right. So that's why, like right now, if you, unless you are writing in the memory, if you just keep your read signal up, it would actually simplify your life. So you don't need to worry about this, like when the data is coming and if it is available or if it is gone even at that point when you are trying to decode your instruction. So I would keep the memory in the read mode except when I'm writing.
okay, memory in read modes. Okay, so yeah, so I did that for like the instruction decode and the instruction fetch. So I set both of those for the memory to be in the read mode. So I should do it for all of the. So you're saying I should do it for all of the
Yeah,
stages that are not read, just to be sure.
yeah, it's no harm unless you are writing, right? If it is a mem stage, you're writing back into the memory. At that point, you need to change the control signal to zero, sorry, read zero, write one. And then after that, on the write back stage, you need to bounce back from there.
Mhm.
So, yeah.
Okay, and so like the inputs that are coming into the control unit at the like the edge of the clock when we're changing the controlled signals,
Mhm.
when we use those inputs into the control unit, we're taking those values from the last cycle, right?
Right, right.
Okay,
Conceptually, you are right. Yes.
okay, okay, thank you.
Hey, Professor.
Yes, friend.
Somebody just told me that you told them that we're not allowed to in our control unit, just or in our ALU, just actually change the opcodes to be the actual CS147 DV opcodes.
No, like, okay, there is this misconception of ALU's code and the opcode for the instruction. They're not the same.
They're not the same, but what's the problem? It takes away one step of conversion if you change the ALU codes, whatever you want to call them, to be the same as or to correspond with the R type instructions, the non shift ones at least.
Well,
So
okay.
that's fine, right?
Yes.
Because then it just reduces, like, it means one less big switch statement where you have to say, like, if it's addition, you have to do 20 to 1 or whatever it is. I would have to look at the instruction set.
Yeah,
that's fine.
Yeah, I think yeah, if it is working okay, then that should be fine.
Okay.
Yeah, because we don't test the ALU by itself. Yeah.
Okay. Cool. Thank you.
So that means you are actually modifying the ALU's behavior, right? And
yeah, but like and then taking that modification into account in my control unit, which is the only place in which it really matters.
right. So you are kind of trying to save the switch statement.
Yeah, I mean, I was like, hey, it means a little less writing, so I did it. But then somebody said you weren't okay with it, so I just want to make sure.
Yeah, so in real life, like, it is not a software, right? You need to understand.
Right.
Real life
is true.
Someone gave you ALU as it is as a hardware component, and you cannot just go and change inside that hardware to take, like, whatever code you like to do, right?
That's a good point.
So that's the things you need to, like, it's a kind of a mindset thing, basically. In the software world, yes, everything we can change as we need, but in the hardware real world, that is the hardware designer pain, because they cannot change as it go. Because once it is done, basically. It's the firm component, you cannot change.
Makes sense. I totally understand what you're saying, and that's good to keep in mind, like for a job and stuff. But just for the projects, is it all right? It's a change stuff that came from the previous project.
Mm-hmm. Yeah, it is not that I'm going to test the ALU by itself. So, yeah, that may work, but ideally you should not change it. Ideally you should not even touch that code.
Totally get what you mean. All right, thank you, Professor.
All right. So if there is no other question, let me move on to this example of just different access mode, a little bit of that. I think I'm showing it. Okay, so here's a problem. Here is a problem. So we have these, let's say we have a snippet of the memory, and we have all the addresses, and also we have snippet of the register content, right? So this is my, this is my memory, all this from starting from, I think, a location of 10000000 till 000C. And some data are stored in like each location is a byte addressable, let's say. And this is my register snippet at that point. At that point, register contains. Now, first problem is that a direct read from the memory location of this. Okay, direct read from memory location of this. I believe this is kind of incomplete. We should actually say direct word read. Let's say. Okay. So each time we say about a read, it is practically we are trying to read a word. So with that respect, let's say it is following the Little Endian convention. So from this location, so what we'll do, a word read will access from this location the 4 bytes. Okay, access these 4 bytes. And it is a Little Endian convention, means practically your lower address have a LSB and higher address as MSB. So for this case, this is my MSB for the Little Endian, and this is my LSB. So my answer for this guy would become like 0 cross 4 0 0 0 0 1 0. So if it is on the other hand, if it is was a big Endian, so this would be treated as a LSB, and this byte would be treated as a MSB. So in that case, my answer would become like, hey, I just made this guy LSB. Just hold on. Little Endian, this color. Okay, so this one is 1 0. So I write from this direction. Okay, 1 0 0 0 0 0 0 4. Whereas a big Endian, I should actually write the word value this direction, because lower address is the MSB. So it is 0 4 0 0 0 0 1 0. That's what the value would be accessed. Okay, that is a direct addressing, and direct addressing practically means we are accessing directly starting from this address. That is the direct addressing. Okay. Now, next one is the indirect read from the memory location this, right? Indirect memory. So what is that? Indirect memory means we first read that given memory location. So we read it, and we read in a Little Endian in part this problem. So we read basically this value, and then use this guy as a memory address. So this is becomes a memory address for this, and then my data would become these four, right? It will read from this guy, these 4 byte. This is my LSB, and this is my MSB. So for this, my answer would be 028A456B6. So this direction I'm writing. This is MSB and this is LSB. The next one, register indirect, read from the register 4. So what we need to do, we basically look at the register 4 content and see where this is pointing to. Like this is the memory address that we should be concerned about, which is like here, right? So LSB, MSB, this way it will be reading. So for this guy, my answer is going to be EB C3 A5. Is it one? Sorry, not this one. MSB4, right? So basically 1, 2, 3, 4 in here. Okay, this is my MSB. So that means this is going to be 2E EB C3 A5. And then the next one is my R6 with a displacement of this. So this value in the 16-bit, it is equivalent to -1 in decimal. So what we need to do, we need to pick up the R6 value, which is this, make a -1 out of that. So that means it becomes 1000A. FE is -1, right? Let me just double check. Programming calculator.
Are you checking if that hex number is -1?
Yes.
It would have to be, right? Because it's just all ones, but then you take
Right.
I thought that would be -2.
Is it -2? I could be being dumb.
Let me see. All F is -1. You are right, actually. It is -2. This is -2. Clear 0 -2. Yep, you're correct. FFE is -2. So this is -2. So -2. So here is -2, which is BA9. Is it 9? Yep, here. So it will read from here to there. So that means for this guy, it will be C3 EB. Other way. But dealing with the little endian. So this will be 132E EB C3. So that would be my answer for this one. Okay. Question?
Should we assume little endianness or big endian on, like, if it's not specified, I guess?
I think default we can use big endian.
Okay, cool, thanks.
Why? Because that's my choice. You know, again, like there is nothing right or wrong there. But I'd say I try to give the Endianness clearly defined in the question. So in exam, if it is not there, it is better to ask me actually, you know, during the exam time. Okay. All right. Then it is mostly this lecture 12 is mostly around these the register accessing and convention of the big endian, little endian, those things, and what are the different components that we need to consider when we are actually writing down an instruction set architecture. So it is more about how to write a good instruction set architecture. Okay. The next one is important concept of the performance measurement. So performance measurement is more like like there are this concept of response time versus throughput. Response time is more like how much time we are spending in a given program. Let's say processor is given a task like to execute a whole program, how much time it takes to from beginning to end, like when you submit and when it completes. That is your response time. And throughput is more from the processor perspective, where it's kind of measured as a how many tasks is done per unit time, let's say per hour, how many tasks are done. So those are the throughput concept. So throughput is more like and whoever is giving the service, and response time or that concept is more like a client perspective. Whoever is receiving the service from that end, that experience is more like a response time. So that is number one. Number two is these. If you have gone through that lecture notes and the videos, you will see this is like an uh, this is a kind of a general guideline for performance related issues and performance related computation. And there are different approximation level, right? We started with, okay, there is this, for example, this average CPI, clock cycle per instruction. So this is really a statistical value that being calculated out of the whole different set of instructions. Means that not that every instruction will need one fixed number of cycles, unless it is a RISC style processor. That's why they're simple, because they assumed a fixed number of cycles. Their CPI is always constant. But if it is a CISC style of design, then there can be different classes of instruction which takes different set of cycles. That means what we can do statistically compute that what is the average number of cycle I can expect if I throw an instruction to the processor. So that is one approximate average level, right? And then we come down to more little bit detail, like class A, class B, class C, different classes of instruction. They take this much average CPI. They are again statistical data, basically, okay, from that perspective. So it has more granularity level of this information as we go down. It is more about how detailed is that model, like how if it is a complete average CPI or it is basically class based average CPI. Depending on that, your performance analysis result will differ. Of course, then ideal measurement is to run a real programs, right? Uh, like they're called a benchmark program practically. So and there are big companies that are there whose sole job is to provide benchmark programs to all the processor house. Like, and they are targeted for different business classes, like web surfing, graphics processing, or pure scientific calculation. All these different classes of benchmark programs are there, and not all the processors are targeting all of these benchmarks. Like they may be targeting a graphics market, or they may be targeting a supercomputing market, or they may be targeting a web market. So based on that, they go with the specific benchmarking program. So those are the real program, and they need to prove that and publish, of course, their performance number based on the benchmark data, benchmark program. Okay, so that is the ideal way. But like till we actually design a processor and send it to the fabrication house, get the real chip back, we cannot really predict or at least test hands-on how the program will be will be performing. And that's where this computer performance measurement theoretical discussion comes in place, where all these statistical informations are gathered and kind of predict that if we go with this kind of architecture, this kind of implementation, it should be giving us this performance edge or performance benefit. Okay. And based on that analysis, a specific architecture is fixed, implemented, sent to the fabrication house, chips comes back, system is ready, then it goes into that field testing with the benchmark program. That's where we see what is the real impact of the performance improvement. Okay, so benchmark is kind of a program which gives the final stress testing for a processor, and everything before is practically a theoretical prediction, just a theoretical prediction. Better theoretical prediction, okay, we are sure that when the chip comes back, it will perform as our target. If the theoretical analysis is not good, then probably we can end up and lose the market, all it is, lose the business, all it is. So it is very important to understand that kind of concept, and going forward, we'll more be dealing with the computer performance improvement. Question? Okay, then let's do another problem related to the performance computation. Those are a little bit of maths involved. Okay, let me share. This problem goes like this. Let's say okay, so let's say there are two computing systems we're trying to compare the performance with, and it says that it's one is running on a 1 gigahertz clock, and another system is running on a, so one is running on a 1 gigahertz clock, and another system is running on a 1.2 gigahertz clock. So that's period, like from the clock speed perspective. Now both are supporting 4 types of instructions. Okay, so both are supporting 4 types of instruction ABCD, and I'll give you the table, CPI table, which is missing here. So why don't I just draw the CPI table for you? So what it tells that I have this class of instruction A, B, C, D, and system X and Y, their CPI data is like 4. So this is my CPI, okay, for both of them. So 4213, and for Y, this is 3132. 3132. Okay, so we have this the CPI table. Now compare the performance between these two systems, that there is a one benchmark program, which is a mix of 25% of type A, 25% of type B, 30% of type C, and 20% of type D. So how much performance gain, like PY versus PX, by this system? So we all know, like PY, performance Y to performance X, is nothing but execution time by system X by execution time of system Y. All right. So all we need to calculate these numbers, execution numbers, and we all know this one is total number of cycle. Like let's do a CX multiplied by time period. This would be number of cycles and time period. So this time period we can calculate out of this frequency of the clocks, right? What we need to do is that compute the number of cycles. So let's say like benchmark program B has n total n instructions. So that means B has how much? Okay, class A instruction is how much? They are 0.25 multiplied by n. Similarly, class B has 0.3 multiplied by n. So I'm using this information 25. Oh, B is 25. Sorry, B is 25. So this is 0.25 multiplied by n. Class C is 0.3 multiplied by n, and class D is multiplied is 0.2 multiplied by n. Now that means my CX cycle total number of cycle for the X would become like 0.25 multiplied by n multiplied by CPI, clocks per instruction, that type A, right, which is 4, plus 0.25 multiplied by n. Then we look at the CPI for the B, which is 2, plus next one is 0.3 multiplied by n multiplied by CPI of 1.
Plus 3.
Yes. Is there a question? Okay. And then next is 0.2 multiplied by n CPI 3. Okay. Which is, if we compute, it is more like to be coming out as a 0.25, 0.25 is 0.5, this is 0.3, 0.8, 0.6. No, what am I doing? Oh, we need to multiply. So this one is 1.0n plus this one is 0.5n, this one is 0.3n, this one is 0.6n, which is 1.5, 1.8, so 2.4n. Okay, 2.4n. Similarly, we can calculate the CY, which is 0.25 multiplied by n multiplied by the system-wide CPI for A, which is 3 plus 0.25 multiplied by n multiplied by 1 plus 0.3 multiplied by n multiplied by 3 plus 0.2 multiplied by n multiplied by 2, which is 0.75n plus 0.25n plus 0.9n plus 0.4n, which is like 1.9, 2.3n. Okay, we have almost all the information. Now what we need to do, compute the TX, which is like given 1 gigahertz. So it will be like 1 by 1 gigahertz. Which is like 1 nanosecond. And this guy TY is given 1.2 gigahertz, so 1 by 1.2 gigahertz, which would be like, let's see, if we just use a calculator. Let's see. 1 by 1.2, 1 by 1.2. 1 by 1.2. which is approximately 0.83 nanosecond. So let's stick in this number there then, 2.4 n multiplied by 1 nanosecond, and here is CY 2.3 n multiplied by 0.83 nanosecond. So nanosecond unit will nullify it. So ultimately it becomes like 2.4 by 2.3 multiplied by 0.83, which is 2.3 multiplied by 0.83 is 1.909, which is, okay, 2.4 by 1.909, which is about 1.257. So your performance of Y is 1.257x better than performance of the system X. Like more likely it is like more or less like 26% improvement.
Professor,
Yes.
why are you even multiplying by n?
This one just to keep our concept steady.
Oh, okay. Is there ever going to be a case where the n's are different between x and y?
Not really, because you always use the same benchmark program, same benchmark.
Okay,
Yeah.
thank you.
Yeah, but if there is an absolute problem, for example, we know that there are like, let's say 4 million instructions in the benchmark, and then there can be a problem, compute the total runtime given this CPI table. In that case, you need to actually do this, not for the comparison purpose. Okay, all right. Now next, do a little bit on the next problem. What's the time? 8:12. Okay, let's take 5-minute break. About 8:17, we'll be back. Okay, let's get back to our discussion. Um, Before that, why don't we have a pop quiz? Please go into your canvas and let's see. Whenever you are ready, please make this yes to this, ready to enter the password. Then I will share the password. Okay. Okay, we have about 41 of 77. Twenty more. I'll wait for like a couple of more seconds. 72 of 76. I think that's good enough for me. Okay, let me share the password. Here it go in this poll. Okay, quiz password. Launch. Okay, I think for most of you is done with the quiz. You can let me look at the stat of the quiz tonight. Okay, so average 67%, which is better than last quiz, pop quiz. High score 100%, that's good. Average time, okay, we don't care about those things. But well, let's keep it up, okay? All right, now
Oh, hey,
let's,
Professor,
yeah,
would you be able to unmute it? Or yeah, I think it's
yeah,
still muted.
I will do that, I will do that. But
Awesome, thank you.
let's move this thing forward on this class. Basically, now you guys need to do this problem in a group. So this problem is that it's based on the previous problem. So let's say these two systems, two different companies, let's say Intel and AMD, for example. And now it is telling that your system X is definitely trailing behind, and they need to respond to that market threat. For doing that, now the compiler team of system X, they realized that all type of A instruction used in the benchmark program can be converted to type C instruction using two of the type C. So each instruction A will be replaced with two instruction type C. Now, if they change their compiler to implement this type A replacement, what would be the new performance gain by this system Y? Like we'll still need to compute this Py by Px, but in this case, we need to consider the compiler change that brought into market with the system X. So I'm opening up the breakout room for 10 minutes, discuss among yourselves, then we'll get back and discuss the result. Okay, so I think break room time is over. All are joining in into the system. So anyone wants to go with the solution? I have opened up the share screen feature. Now you can share your screen if you want to show the solution. Anyone wants to go volunteer? Okay, no. Okay. All right, then let me try to do it. Okay, this one. So this is an easier side of the problem. So what is being done here is asked here is this, right? So you are replacing all type of instruction A with the type of instruction C using two of them. That means if you look at the previous solution, when we were computing about the CX, about the CX, we had this part, right? This part to calculate on. So this means like we are replacing, this is for, remember this was for the type A, and this 4 was coming from here. So this problem is practically saying that replace that 4 with 2 of number C, right? 2 of C. So practically we are trying to replace this with 2 CPI, basically. Not 2 CPI, 2 multiplied by 1. Each of the instruction will be replaced by 2 of the C instruction, and each of the C instruction has 1 CPI. So that is what it is coming out as a 2 multiplied by 1. So that means this guy will become 0.5. That means 1, 1.3, 1.9. So this becomes 1.9. Whereas CY will be same because no compiler changes them down on that side. That means I will have 1.9 over here, which means for that one, so it's almost close actually. In fact, 1.909, it is 0.995. So for this guy with the compiler improvement, my py by px is become like 0.995. That means px is a little bit better in fact in this scenario. It's no longer trailing the py, so that means they actually saved their business in the field. And in fact, this is a real life scenarios where your performance improvement is not just tied with the hardware improvement or tied with the software improvement. It is tied with the both. And each processor house has dedicated compiler team. Actually, they provide compiler. Like Intel has an Intel compiler, AMD has an AMD compiler, and so on and so forth. And they actually provide all these tuning libraries towards the software programmer to make best of their performance improvement in a system overall. So that is the whole ball game. Like neither hardware team nor the software compiler design team go alone in the field and to play in the field, but they go together and optimize things. Even hardware is slower, compiler team can do some tricks there to look it better. Question?
Can I ask a question about the project again, like the cycles?
Yeah.
So about like the code in the Verilog. So when the cycle changes, the state changes. Like the state changes too. So I have to change all the control signals. So is it at that clock when I
Yes.
change all of the control signals? Only
Yes.
after that does the memory and the register file use those control signals in order to determine in order to like find their data, do their like read data or write.
So
Is it-
control signal has changed as soon as the state is changed, right? And
Mhm.
your main part, like your action is based on in the control unit, your action is based on the state, not on the clock. Your state is changed on the clock,
Mhm.
right? So as soon as you change the state, you need to change the signal corresponding to that state.
Mhm. So yeah, but at that exact same time, like the register files and the memory is supposed to do their operation at that clock too. But at that clock, we're also changing the signal. So is it that when we at that clock when we change only after we change those signals does the register file and the memory do their operation? Like
As soon as I said, it's a zero delay model. So as soon as it receives the signals at that point, it will act on that. So you might want to look at the timing diagram and little bit understand this zero delay concept and what is going on in the system. So is there anything specific that you are facing problem with, or it's more like an conceptual?
right now is more conceptual. Also, there's something about the like the do we need to use like the non-blocking assignments, because I've just been using blocking assignments. So and I think I need blocking assignments for some parts, like in
Yeah,
the instruction.
I don't think you need to do any non-blocking assignment so far as this project is concerned.
Okay.
If you need, definitely you can use it. Definitely you can use it, but I don't think you need to.
Okay, and one last question. It's about like the thing you said where when you go to when you make the control signals for the next state, then then if you're using like the inputs for the control signal, like you're using it as like one of to assign the new control signals, you use the input for the control unit. So in that case, does that mean that when I go from instruction fetch to instruction decode, I don't need to like make the memory into keep the memory at a read. So on instruction decode, can I change the memory into into a hold condition? And
Ideally, you can. Ideally, you can. It depends on what this memory model is doing on the hold condition, whether it is holding the previous data or not.
mhm, because because when you said that like on the decode phase, like the data in like let me see, the data from the memory goes into that instruction register. So it's taking it from the previous cycle. It's taking that memory from the previous cycle. So if on the decode cycle I just leave the memory on hold, then it would be then like afterwards it would be like outputting an unknown value. But I already took that data from the last cycle, on which it
No.
was being
Why do you want to take the risk instead of if you just set it to read, your address is not being changed. So that means your data will not be changed and you will not to deal with the unknown values there in this model. So you're saying that in this model, if you make it a hold mode, the output of the data path going X.
I'm saying like so if you make the data, if you make the memory at instruction decode, if you
Mhm,
set that to a hold condition,
mhm.
I'm saying will it I don't think it will affect like the what's loaded into the instruction register, because what the instruction register is getting is the value of the memory like the data from the previous from the instruction fetch cycle. So
Yes.
it's just like a theoretical question. Like I'm going
Yeah,
like
yeah. So now the question becomes, how do you want to model it in the very, right? If you model it correctly, then you should be okay.
mhm.
Like theoretical concept is all right, I see here. It's all depends on how you're modeling, how you're writing it into the Verilog code, that is now the important part. Concept-wise, you're I think okay.
Okay. All right. That's all I have to say. Thank you.
Okay. All
Professor, I
right.
have a very quick question on project 2.
Sure, Manu.
Okay, so in the guideline, it says that for the control unit, we need to add registers for corresponding output ports. Do those registers need to have different names from the names of the output ports, or
Can have the same name.
they can have the same name? It doesn't really matter.
For the output port towards the memory, right? Is it?
I think so. I
Memory
don't have it in
data
front of
is
me.
a different business. Memory data path, because you need to keep it to the high Z if you are reading from the memory. So that means you cannot have same registered name as the port name of the memory data, that port. Okay.
Yeah.
Other than that, if it is just a unidirectional output port, then you can make the register as the same name. But
Okay.
memory data is a bidirectional port, so you cannot have the same name. You have to drive it depending on the read or write condition.
Okay, so the memory is the only one that has to have a different name?
Right.
Okay, thank you.